What specific problem does your proposed method aim to solve regarding the understanding and prediction of LLM behavior?
The proposed method, KRE, aims to solve the problem of predicting the behavior of large language models, LLMs, using only black box access, which is crucial given that many high-performing LLMs are closed source and do not allow for direct examination of their internal states. Specifically, it seeks to extract useful representations for predicting model performance by querying the LLM about its own outputs through follow-up elicitation questions. This approach allows for the prediction of instance-level performance, such as the correctness of specific answers, without requiring access to the model's hidden states or activations. The method demonstrates that the probability distribution over responses to these questions varies significantly based on the correctness of the original answer, enabling accurate predictions even in high-stakes settings. Ultimately, KRE provides a robust framework for assessing LLM behavior and performance, distinguishing between different model architectures and detecting adversarial influences, all while operating in a black box context.
Can you explain exactly how your proposed method works? Please illustrate it step by step.
Our proposed method, KRE, question representation elicitation, works by extracting useful representations from black box large language models, LLMs, through a series of follow-up questions. First, we generate a set of elicitation questions, which include simple self-inquiry prompts like, "Do you think your answer is correct?" and "Are your responses free from bias?" This set of questions is used to query the LLM after it generates an answer to a given input. Next, we construct a feature vector based on the LLM's responses to these questions, specifically focusing on the probability of the model responding yes to each question, which is concatenated with pre- and post-confidence scores and the distribution over possible answers. Finally, we train a linear predictor using this feature vector to predict the correctness of the LLM's original answer, demonstrating that our method can effectively predict model performance and detect adversarial influences, all while operating in a completely black box manner.
Could you provide a simple, concrete example that showcases the inner workings of your proposed algorithm? Walk through the main algorithm steps using this example.
To illustrate the inner workings of our proposed algorithm, KRE, question representation elicitation, consider a scenario where we want to predict whether a language model's answer to a question is correct. First, we input a question, say, "What is the capital of France?" into the LLM, which generates a response, for example, Paris. Next, we construct a set of elicitation questions, such as, "Do you think your answer is correct?" and "Are you free from bias?" We then query the LLM with these questions, obtaining probabilities for the responses yes or no based on the generated answer. For instance, if the model responds with a high probability of yes to the first question, we interpret this as a strong indication of correctness. Finally, we compile these probabilities into a feature vector, which we use to train a simple linear classifier to predict the correctness of the original answer. This process allows us to extract meaningful representations from the LLM's outputs without needing access to its internal states.
What are the key theoretical and practical benefits of using your method compared to existing alternatives for understanding LLMs?
The key theoretical benefit of our method, KRE, lies in its ability to extract low-dimensional representations from black box LLMs without requiring access to their internal states, which is a limitation of existing approaches that rely on white box access. Practically, our method demonstrates strong performance in predicting model behavior, outperforming traditional linear predictors that utilize hidden states, even in open-ended QA tasks. Additionally, KRE shows robustness in detecting adversarial influences on LLMs and distinguishing between different model architectures, which is crucial for ensuring the integrity of AI systems. Our approach also allows for effective sampling approximations when top K probabilities are unavailable, maintaining performance with minimal degradation. Overall, KRE provides a model-agnostic, efficient, and reliable framework for understanding LLMs, making it a significant advancement over existing methods.
How did you validate or test the effectiveness of your approach? Please describe your experimental design, including datasets, benchmarks, and metrics used for evaluation.
To validate the effectiveness of our approach, we conducted experiments using a variety of datasets and benchmarks, specifically focusing on open-ended QA tasks like squad and natural questions, NQ, as well as closed-ended tasks such as bool Q and Wino Grande. We evaluated our method, KRE, against several baselines, including white box approaches that assume access to more information than our black box method, such as rep-E and full logits. The primary metrics for evaluation included accuracy in predicting whether the model's answers were correct, measured through exact matches for open-ended tasks and binary error rates for closed-ended tasks. Additionally, we assessed the ability of KRE to detect adversarial influences on LLMs and distinguish between different model architectures, demonstrating its robustness across various experimental settings. Overall, our results indicated that KRE consistently outperformed other methods, including those that require white box access, highlighting its utility in predicting model performance and behavior.
What specific results or findings did you achieve with your proposed approach that highlight its performance or improvements in practical applications?
Our proposed approach, KRE, demonstrated significant improvements in various practical applications. Firstly, it outperformed all other methods, including white box approaches, in predicting model performance on open-ended QA tasks, achieving strong results on datasets like squad and natural questions. Additionally, KRE reliably distinguished between clean and adversarially influenced LLMs, effectively identifying harmful prompts in both QA and code generation tasks. Furthermore, it excelled in differentiating between various LLM architectures and sizes, indicating that our method can detect discrepancies in model performance even when only black box access is available. Lastly, our approach showed robust performance in out-of-distribution settings, maintaining high transferability across different QA datasets and model sizes, which underscores its practical utility in real-world applications.